we've studied about polynomials and roots, and we're now ready to jump into linear algebra once again. Okay, what is the connection? Why do we need all this? And this is the crux of what we're going to study in this lecture: invariant subspaces, eigenvalues, and eigenvectors. Okay, so these are very important, very crucial, central ideas in the study of linear operators. This is what makes operators more interesting and much more easy to work with and deal with. Eigenvalues, eigenvectors are so crucial in applications, they show up all the time. Okay, so you have to have a very good understanding of where they come from. So let's start looking at it. We'll study them in multiple ways. We'll spend at least 2-3 lectures on them, look at various applications, how to think of them, where they, what is the correct way to imagine these things. And this notion of invariant subspaces, their connection to eigenvalues and eigenvectors, is the central idea in this whole eigenvalue definition. Okay, so let's jump into it. Quick recap, it's the same as before, so I'm not doing much of recap in this lecture. So let's jump into invariant subspace. Okay, so what are we studying? We are studying operators from V to V. There's a vector space V over a field F as usual, and there's an operator, linear map, linear operator, which goes from V to V. Okay, we will say that a subspace of V is invariant under this operator T. It's a sort of an obvious definition. We say invariant, it doesn't vary, right? It does not change. If the operator acting on that subspace results only in vectors inside that subspace. Okay, so if for every u in the subspace capital U, T times U belongs to that same subspace. Okay, so that's the picture. If you want a picture, you can draw a picture. So I have V, and then I have another copy of V, and I have my T going from V to V in general, but guess what, there is a subspace U and I am calling it invariant. The same subspace will be here also, right? So T should not leave U. Okay, so while T takes V to V, this subspace, invariant subspace U, is special because T, after acting on vectors in U, does not get outside of U. Okay, it keeps you inside U. Okay, so this is sort of interesting. Now, the first example I have put here is a very simple example. I am talking about the identity map, right, 1001. I have shown you that R2 is invariant, but that is a sort of a trivial example, right. For any operator, the entire V will be invariant. Okay, so it is not so interesting, but what about this identity map? In fact, for the identity map, any subspace is invariant, isn't it? What does the identity map do? It does not do anything, it maps everything to itself. So you take any subspace. What are subspaces in R2? Lines through the origin, right. So every line through the origin, identity map remains the same. Okay, so identity map is sort of like a trivial example, and notice whenever we looked at operators, we like maps with like this, right. So the operator like this is very easy to understand. Identity, lots of zeros in the off diagonals, only the diagonal is non-zero. We really like that, and we already see that form is very helpful in terms of invariance. So when you have identity map and the identity matrix, a lot of subspaces seeming to be invariant. So maybe you know, we are looking for such things. So maybe this invariant subspace has some connection. We'll see this connection soon enough, but this is important to know. Okay, so this is the first example. The next example is again diagonal. Notice we like diagonal matrices, right? Diagonal matrices describe very simple operators. Okay, diagonal matrices are nice. Once again, we see that there are a lot of invariant subspaces. Okay, in fact, if you look at span of 1, 0, okay, the x-axis, that's invariant. Okay, span of 0, 1, the y-axis, that's also invariant. Okay, so notice what happens. So how do I sort of confirm that this is invariant? You can check this. It's not very hard. So you see it's diagonal. When I multiply with 1, 0, what happens? Okay, I get 2, 0, which is 2 times 1, 0. Okay, so this is what's most important. So any vector in the x-axis is going to be some x times 1, 0. So if I operate 2, 0, 0, 3 with x times 1, 0, what am I going to get? 2x times 1, 0. So I don't go outside of the subspace. Okay, invariant. Same thing with 0, 1. Okay, so if you multiply by 0, 1, you're going to get 0, 3, which is 3 times 0, 1, so it becomes invariant. So we see that this is a diagonal matrix, very simple with lots of zeros, and it has lots of invariant subspaces. Obviously, one can notice that they are there. Okay. Now, what about other types of cases? What about a matrix like this? 1, 2, minus 1, 4. Do we have invariant subspaces? Okay. How do we find invariant subspaces? Is it easy to find? And do invariant subspaces help? Will invariant subspaces help you in simplifying the matrix associated with this linear map? Will you get something better? Okay. So, let us see this example, this particular example a little bit more closely. I will give you the answer for this and we will talk about why that helps, etc. And then we will look at how to find those invariant subspaces and look at them, define things properly and do it properly. So, here is the answer and why invariant subspaces, why they are interesting. So, it turns out for this 1, 2, minus 1, 4, there are in fact two different subspaces which are invariant. Okay. So, what are the invariant subspaces? So, let us look at the first one, 2, 1 apparently is invariant. Okay. So, let us check that. Can you check it? It is not very hard. So, if you do this 2, 1, what am I going to get? I get 4, I get 2, which is 2 times 2, 1. So, you see that this is invariant, isn't it? You start with any multiple of 2, 1, you are still going to get a multiple of 2, 1. Okay. Same thing with 1, 1, you can check that. When you multiply with 1, 1, you will simply get 3, 3, which is 3 times 1, 1. Okay. So, we see that this matrix, while it is not apparent immediately that maybe you can't quickly guess 2, 1 and 1, 1, I am not expecting you to guess. By the end of this lecture, you will be able to find this, but still at this point, even though this does not have so many zeros and it is not very clear how I got this, but somehow once I give you, you can check very easily that these are indeed invariant subspaces, and there are two of them, two one-dimensional invariant subspaces. Now, what is the big deal? What happened because I had these invariant subspaces? Here is what happens when you have lots of one-dimensional invariant subspaces. Notice what happens. You can do a change of basis. How do I change basis? We know how to change basis. Okay. For this operator 1, 2, minus 1, 4 in the standard basis, I am going to change basis to 2, 1 and 1, 1. Notice where I got 2, 1 and 1, 1 from. Those were the basis vectors of the one-dimensional invariant subspace. Notice what happens when I do 2, 1, 1, 1. In this spaces, the linear map T, the operator T becomes diagonal. Okay, 2, 0, 0, 3. It is very easy, it is obvious, right? What is the first column of the matrix? It is, right, the first basis vector transformed by T, T times V1 represented in the basis B. Okay. If this V1 is invariant, what is going to happen? It is simply going to get scaled, and when something gets scaled, I get a diagonal matrix representation. Okay. So, you can see it will be just 2, 0 and 0, 3. So, everything is only getting scaled and you get an obvious diagonal matrix. Okay. So, this invariant subspaces in particular, it seems like this invariant subspaces will give you lots of zeros on the associated matrix when you go to the suitable change of basis, and that is very promising, and this is something that we wanted to do, right. When you given a linear operator, maybe it has a lot of non-zeros off diagonal and you are confused about what it is doing to your various coordinates. It turns out if you find invariant subspaces, there is some hope. Okay. And notice this is the same basis, right. Input basis and output basis is 2, 1, 1, 1. I am not changing the input basis and output basis, I am keeping it the same, and I get 2, 1, 1, 1. When I change to that basis from this basis, I get a diagonal matrix 2, 0, 0, 3. Okay. So, that is very nice to see, and that is very promising. So, these invariant subspaces are something very important to study, and they are very crucial to understand operators. Okay. So, let us get going and figure out how to find these things. How did I find 2, 1 and 1, 1? I will show you how I did it. It's quite easy. Let's see that, and that will lead us naturally to this definition of eigenvalues and eigenvectors. Okay. So, eigenvalues are closely associated with one-dimensional invariant subspaces. So, let us do the setting carefully. I have an operator T from V to V. I will assume it is finite dimension, and there is a matrix A associated with the linear operator T in some basis. You pick your favorite basis and you have a matrix A. Okay. So, let us say you have a one-dimensional invariant subspace. Okay. So, span of V, right. So, there will be one vector V and its span is the one-dimensional invariant subspace, let us say under T. Then what will happen if I do T times V? T times V has to be equal to lambda V. Okay. So, there should be some lambda such that T times V is equal to lambda V. Okay. What about the other case? Supposing V is a non-zero vector. Okay. So, V is non-zero. So let me also put that down here, V non-zero, okay. And so I've put if and only if here. So if suppose V is non-zero and TV equals lambda V, then what happens? Span of V is the one-dimensional invariant subspace. It's easy to check, okay. So you notice that having a one-dimensional invariant subspace is similar to looking at this equation TV equals lambda V, okay. So these are the same things, okay. So and that's crucial in our upcoming definition of eigenvalues, okay. A scalar lambda, eigenvalue is a scalar lambda from the field F is called an eigenvalue of T if there exists a non-zero vector V such that TV equals lambda V, okay. There should be a non-zero vector V which when T operates on it only gets scaled, does not change to something else. You can draw a picture if you like, you can visualize if you like. I want a vector V, a non-zero vector V, which when T operates on, you should get a scaled version. You should not get some other combination. No other combination is allowed. Every coordinate should only get multiplied by the same constant, okay. So if that happens, that constant value lambda is called an eigenvalue of the operator. So notice I am talking about operator here, not any particular basis representation. We will come to that soon enough, but this is what the property is, and you can see eigenvalues are closely connected to one-dimensional invariant subspaces. So in short, if I can find an eigenvalue, I have found a one-dimensional invariant subspace. And if there is a one-dimensional invariant subspace, there has to be an eigenvalue, okay. Both of these are connected, okay. So hopefully this definition made sense. So naturally the next question is, do these exist? Do eigenvalues exist? So let's look at this equation a little bit more closely. If TV equals lambda V and V not equal to 0, you can push lambda V to the other side. You are going to get T minus lambda I. Now notice this identity map enters the picture, times V equals 0. So this is the same as that. You multiply V inside, you get TV minus lambda V equals 0, right? It's the same equation, and V not equal to 0. Now this is possible if and only if T minus lambda I is non-invertible, right? So see, notice T minus lambda I times V should be 0 and V should not be 0, which means the null space of T minus lambda I should be not empty. Okay, it should have a non-trivial null space. Only then this is possible, right? And which is also equivalent to T minus lambda I being non-invertible, right? We know we are in a square finite dimension world, so this is equivalent to this, isn't it? So this is a very simple condition. So lambda is an eigenvalue if and only if T minus lambda I is non-invertible. Okay, so that's a very nice result. Null of T minus lambda I has to be non-trivial. Only then lambda is an eigenvalue. Okay, so that's nice to see. Now this non-invertibility we can deal using determinants very easily, right? So T minus lambda I is non-invertible if and only if determinant of A minus lambda I equals 0, right? A is a matrix with respect to some basis. Now I am going to some basis. So far I was only with linear maps. Suddenly I am picking a particular basis. We will see quickly that this is not a problem, but anyway, but this is something I can do. I can pick a basis, then look at determinant of, pick a basis, pick a matrix, and then look at determinant of that matrix minus lambda I. That should be equal to 0. Now what is determinant of A minus lambda I? Looking from the formula, looking at the cofactor expansion, etc., you can easily see that determinant of A minus lambda I is a polynomial of degree n in lambda. Okay. So where did we go from? We started from invariant subspaces and defined something called eigenvalue. And what are eigenvalues related to? Roots of a polynomial of degree n. Okay, how do you find that polynomial? You go find a base matrix for that linear map in some basis and then take determinant of A minus lambda I. You will get a polynomial in lambda of degree n, and that polynomial's roots, you go to the complex field or whatever field that you are in, you find the roots, and those are all eigenvalues for the linear map T. Okay. So now why do I keep saying linear map T while I have a matrix A? What if I change basis? What if this matrix changes? Will this polynomial change? It turns out the polynomial will not change. That also is something we can quickly see. The eigenvalues do not depend on the basis. Whatever basis you pick to find the matrix A, you will get the same eigenvalue. Why is that? Because if instead of A I did some other basis, I know it will be of the form S inverse AS, right? S is an invertible that operator, change of basis operator. But if you look at this determinant, you can pull S inverse and S out on both sides because this is identity. I can pull it on both sides, and what do I know about determinants? Determinant of a product is product of the determinant, and what is determinant of S inverse is 1 by determinant of S. That will cancel, I get the same thing. Okay. So this determinant A minus lambda I, it does not matter what A is, whatever basis you pick, you get the same polynomial, you get the same eigenvalues. Okay. So this one slide sort of captures a lot of things that are important about an operator. Given an operator, we know that one dimensional invariant subspaces are good, they seem to give us nice matrices, that is very promising. How do I find these one dimensional invariant subspaces? I have to find eigenvalues, okay, because eigenvalues are directly related to invariant one dimensional invariant subspaces. And how do I find eigenvalues? They are roots of a polynomial of degree n. Okay, you go find the roots, you know eigenvalues are there. Okay, so soon enough we will see a version of this without determinants also. Okay, and in the next lecture we will see that, but this is the classical way in which eigenvalues are introduced to show existence and how one can think of them, etc. Okay, but we will come back and define eigenvalues in a different way. We will study them more closely than this, but right now this is a good way to introduce eigenvalues. Okay. All right, what are eigenvectors? Okay, so eigenvectors are very closely related to eigenvalues. It's just almost there. I'm putting it out as a separate definition here. If you have an operator, a non-zero vector v is called an eigenvector corresponding to an eigenvalue lambda if Tv equals lambda v. Okay, so that other v, right? So in the previous equation Tv equals lambda v, we defined lambda as the eigenvector, eigenvalue, v is the eigenvector. Okay, so anyway, every time you think of an eigenvalue, you should also have an eigenvector. Without that, there is no question of an eigenvalue, right? So the other part is the eigenvector. Okay, so that's the eigenvector. So we see very easily that if v is an eigenvector, then any scaling of it is also an eigenvector, right? Of course, you shouldn't put 0. Any non-zero scaled version of an eigenvector is also an eigenvector. So these non-zero scaled versions we will not distinguish. Just because we have multiple non-zero scaled vectors, we will not keep adding them to the eigenvector. I mean, they are all eigenvectors. We can think of them as eigenspace or something like that, but they are not really distinct or new in some case. The reason is they correspond, they are not linearly independent from this other guy, right? But for the same eigenvalue lambda, you may find linearly independent eigenvectors. If you find linearly independent eigenvectors, it's still interesting, okay, because then from just by scaling you won't get them, okay. So you have to find linearly independent eigenvectors. I'll comment a little bit more on this soon enough. But notice one very easy thing. How do I characterize eigenvectors? Eigenvectors of lambda, once we understand we only want linearly independent eigenvectors, is simply a basis for null t minus lambda I. Okay. So why am I saying basis? If I want all eigenvectors, then all possible scalings also if I accept, then the entire null space of t minus lambda I is the eigenvectors except for the non-zero vector. All non-zero vectors in, maybe I should write that down, all non-zero vectors in null t minus lambda I are eigenvectors of lambda, right. So this is definitely true according to the definition, but when we write down, usually you don't want to write all possible eigenvectors, right. So this might be infinitely many of them. So we simply stick to the basis, okay. Just write the basis and say that span of all these things is also eigenvectors, okay. Span of eigenvector is also eigenvector. So you can simply say basis of null t minus lambda I, okay. So given an eigenvalue lambda, I know t minus lambda I has a non-trivial null space, right. You go find the basis of that null space, you get the eigenvectors, description of all eigenvectors, alright. So this is the way to find eigenvectors, okay. So eigenvalue, you solve a polynomial roots, find roots for a polynomial. For eigenvectors, you do your familiar thing, okay. So you know an operator, you have to find the null space of an operator, you know how to find null space, right. You just use that same method, you will find the basis for the null space. Okay, so let's see a whole bunch of examples. Okay, so we'll see very simple examples. I'll only do 2 by 2 at least in class. You can do maybe more examples with larger matrices. In your assignments, you may have more examples for getting practice. But anyway, today you just go to a computer and ask it to give you the eigenvectors of a matrix, it will give you. Okay, so you don't need eigenvalues and eigenvectors, you can find. So it's not a big deal to calculate these by hand, but they give you some, the purpose of me doing it is to illustrate to you what are the various things that can happen. Okay, so you will see some interesting things can happen. So let's begin with the diagonal matrix 2 0 0 3. Determinant of A minus lambda I is 2 minus lambda 3 minus lambda. So the roots are simply 2 and 3. Okay, one can easily see the roots are 2 and 3, and the eigenvalues are 2 and 3. Okay, so easy. How do we find eigenvectors? For eigenvalue corresponding to 2, okay, so eigenvalue corresponding to 2, it is the null space of A minus 2i. What is A minus 2i? 0 0 0 3. Okay, and for 3, it is the null space of 2 0 0 0 0. Oh no, I think I made a mistake here. Let me just do this. 1 here, minus 1 here, sorry. Okay, so it is A minus lambda I, right. So it is A minus 2i, so I have to subtract 2 from the diagonals, so I will get 0 1 here, and for 3 I have to subtract 3 from the diagonals, so you get minus 1 0. So you can see the null space of this guy, the first one is clearly 1 0, okay, so this is 1 0, and for 3 it is 0 1. Okay, so they have just dimension 1 null spaces. You can see that the matrix has rank 1, no? Rank is 1, nullity is 1. So you have dimension 1 null spaces, and the basis is very easy to find in this case. Okay, very easy example. You know, I keep doing only easy examples in class, but the more difficult examples you will get in your assignments. Okay, the next immediate example we are going to take up is the more complicated example I did, if 2 by 2 can be considered complicated. Okay, 1 2 minus 1 4. You do determinant A minus lambda I, you get lambda squared minus 5 lambda plus 6 equals 0, and lo and behold you get the eigenvalues 2 3. Okay, so now solving for this may be slightly more complicated. Okay, so you have to find you know, for 2 it is the null of, okay, A minus 2i, so you have to subtract 2 from the okay, I think minus 1 2 minus 1 2. Okay, and for 3 it is null of, I have to subtract 3, so minus 2 2 minus 1 1. Okay, so you can see these things work out quite okay. You can see that in the null space for 2 you have 2 1. Okay, so if you multiply by 2 1 you get 0. For 3 the null space is 1 1. Okay, so you can see these are rank 1 matrices and you get 1 1. Alright, so this is how you find eigenvectors, eigenvalues in simple cases. The next case I am going to take up is slightly more interesting. You slowly start getting more interesting cases. The identity matrix. Notice what happens in the identity matrix. My determinant of A minus lambda I has repeated roots now, 1 minus lambda squared, and that becomes equal to 0. So eigenvalues is 1 repeated twice. Okay, that is 1. And what about eigenvectors? The eigenvectors for this is null space of A minus lambda I. So that is 1, so it is just 0 0 0 0. So rank is 0, nullity is 2, so you have 2 basis vectors in the null of this guy, 1 0 0 1. You can take any other thing also, you might as well take 1 0 0 1. Okay, interesting case. For one eigenvalue we got 2 different linearly independent eigenvectors, okay, and the multiplicity was 2. That is good. So let us move on to a general definition now. Okay, so let me give you a general definition. There are 2 types of multiplicities associated with a particular eigenvalue lambda. One is what is called algebraic multiplicity. This is how many times lambda appears as a root in the polynomial determinant A minus lambda I. Okay, that is called algebraic multiplicity. Another multiplicity associated with an eigenvalue lambda is what is called geometric multiplicity. That is basically you have null of t minus lambda I, right. Null of t minus lambda I is the subspace of all eigenvectors. The dimension of that is called the geometric multiplicity. Okay, so in the above example, okay, if you go to this example, algebraic multiplicity equals to geometric multiplicity equals 2. Okay, what about for this guy, for the eigenvalue 2? Algebraic multiplicity equals 1 and geometric multiplicity equals 1. Okay, so these are just examples. You can see more such examples going on. Just definitions. It's nothing big here. There's a more interesting case, and that's the next example I'm going to take up. Let's take up this simple little change from the identity. Instead of putting 1 1 0 0, I put 1 1 2 there, okay. But notice what happens to the determinant of a minus lambda I. You simply get 1 minus lambda squared. Nothing changes because it's upper triangular. You use your determinant method. You know upper triangular matrices also. It's just product of the diagonal elements. So the determinant is only 1 minus lambda whole squared for a minus lambda I. So eigenvalue still has algebraic multiplicity 2, right? 1 repeated twice, algebraic multiplicity is 2. But notice what happens to geometric multiplicity. I need to find for this guy null of 0 to 0 0. Now rank is rank is 1 here, so nullity is only 1, so you will only get one linearly independent one basis vector for the eigenspace. So in some case in this null of 0 to 0 0 you only get 1 0, right. So the geometric multiplicity becomes 1. So now this can also happen, okay. Notice in the previous cases we had algebraic multiplicity and geometric multiplicity being equal. In this case geometric multiplicity became less than algebraic multiplicity. So it turns out that can also happen, okay. So we will see these more interesting results of this type we will see going along, but at least we see that these are all the calculations. So in general what do you do if you have an n cross n matrix? You find out determinant of a minus lambda I, find out the roots of lambda, roots of that polynomial, and then go find the basis of the null space, okay. So that you might think is the method. So it turns out the general case n cross n, you better use modern numerical methods. There are so many tools out there, so many software which can easily find it, and most of them don't do this route, okay. This finding the determinant, finding the polynomial which is determinant a minus lambda I, finding the roots of that polynomial and then solving. That's not the method that is preferred. There are many more powerful methods today, and this is not a course on numerical methods in linear algebra, so we are not going to see all that in great detail, but there are many more methods today which are powerful, and in fact it's so powerful that how do people find roots of polynomials? In many cases you find a matrix for which that polynomial is the determinant of a minus lambda I, and then find the eigenvalues and eigenvalues of that matrix, okay. So there are things like that. So in some sense eigenvalues are more fundamental than the roots of the polynomial in some vague way, because they can be, at least from a numerical point of view, right, let me not say fundamental of course. So from a numerical point of view, finding eigenvalues is much easier using direct other methods, okay. But the determinant is good for small cases, and of course when you have to do hand calculations in quizzes, determinants are extremely useful. So we have to study the determinant approach first. So later on we will come back and see how to think of eigenvalues, eigenvectors in a fundamental way without using determinants. We will see that in the next few lectures, and you will see that's more illuminating. It gives you more ideas about where they really come from. But this notion of one-dimensional invariant subspace related to making matrix of the operator simpler, all of that, and eigenvalues and eigenvectors, and associating it with determinant is not a bad way to study eigenvalues to begin with, okay. So, and like I said, I mean we are not just interested in computing eigenvalues, eigenvectors, we are also interested in understanding what is going on a little bit more, okay. For that we also want to see some theoretical results around eigenvalues, eigenvectors. So the next result we will see is a very interesting theoretical result. The first one we are seeing about eigenvalues, eigenvectors. I will leave you with this for this lecture. I will pick up from here in the next lecture. So here is a very interesting theoretical result on eigenvectors. This is about linear independence, right. If you have distinct eigenvalues lambda 1, lambda 2 to lambda m, and there are eigenvectors associated with each of these eigenvalues. Remember, once I have an eigenvalue, there will be one eigenvector. That is assured, right. Why is one eigenvector assured? That is how I define the eigenvalue. T minus lambda I has to be non-invertible, which means there is some non-zero vector in the null space. I know there is at least one eigenvector out there, right. So I have m distinct eigenvalues, I have m eigenvectors associated with them. It turns out if the m eigenvalues are distinct, then the m eigenvectors are linearly independent, okay. It's a very nice result. The proof is not very complicated. I will walk you through the proof. But notice what this tells you. So if you have more and more eigenvectors, more and more invariant subspaces, they all cannot be linearly dependent. The invariant subspaces of an operator have to be linearly independent. Okay, when you have these linear independence, it's again beginning to look nice, no? I mean, those things then start to form a basis, you know, I mean, all of this is becoming very, very interesting. So this is what's very critical. So let's see a quick proof. So the way the proof works is by contradiction. Okay, sorry. The proof is by contradiction. What is contradiction? If you want to show something is linearly independent, what do you assume? Assume V1 to Vm are linearly dependent. Okay, so proof is by contradiction, so you assume they are linearly dependent. Once you assume they are linearly dependent, what happens? You can use the linear dependence lemma. Okay, so you can see how many times we use this linear dependence lemma, right? It's very fundamental and powerful. So I know that there will be a Vj such that V1 through Vj minus 1, Vj lies in the span of V1 through Vj minus 1. At least one j exists. Now out of all that j, I will pick the least such j and I will call it k. Okay, so k is the least value such that Vk belongs to the span of V1 through Vk minus 1. Okay, so it's sort of a critical choice here, this k being least, and I will get my contradiction on that. Okay, I will say that k cannot be the least. Okay, I'm starting with the least and it cannot be the least, so you'll get a contradiction. Okay, so why am I assured that such a value exists? Linear dependence lemma. I know there is at least one. Out of all that, I will pick the least. So now what does it mean? Vk is a linear combination of V1 to Vk minus 1. Now I know all these guys are eigenvectors, they are not regular vectors, right? If they are regular vectors, I can't do more, but they are eigenvectors. So notice what I am applying. I am going to apply t minus lambda ki. Okay, that operator, notice that operator is very powerful. It's an interesting operator, by the way. So t minus lambda ki, I'm operating on both sides. What will happen to the left hand side? It will go to 0. What will happen to the right hand side? You will get this form that I have here. Okay, a1 into lambda 1 minus lambda k, ak minus 1 into lambda k minus 1 minus lambda k. So notice, not all the ai's will be 0, right? That's the linear dependence lemma. And this lambda 1 minus lambda k, all of these are non-zero. So out of this also there will be something non-zero, right? This ai into lambda I minus lambda k, at least one will be non-zero, which means what? V1 to Vk minus 1 is linearly dependent. If V1 to Vk minus 1 is linearly dependent, you use the linear dependence lemma, there should be something else which is in the span and my k being the least is violated. Okay, so V1 to Vk minus 1, maybe I should write this down. So not all ai equal to 0. So here also not all ai into lambda I minus lambda k equal to 0, because lambda I is not equal to lambda k, right? So the distinct value is very important. So that implies V1 Vk minus 1 is linearly dependent. If it's linearly dependent by the linear dependence lemma, there should be a j between 1 and k minus 1 such that Vj is a linear combination of V1 to Vj minus 1, and that violates, this contradicts this choice of k. K is the least such value, something like that cannot exist, and I have a contradiction. So anytime V1 through Vm is linearly dependent, I am going to have this contradiction, which means V1 through Vm have to be linearly independent. Okay, so that's a nice result to have. So you see that these invariant subspaces, eigenvectors are becoming very, very interesting, particularly when you have distinct eigenvalues. They are becoming linearly independent, and we'll start using these things in the next few lectures to simplify the matrix corresponding to linear map, try to understand it better, try to get a more good feel for what it represents. Okay, so thank you very much.